My name is Przemysław Kazienko from Wrocław University of Science and Technologies, and together with Jan Kocoń, it will be our pleasure to show you our research on personalized NLP. So the agenda is as follows. So we'd like to present you our background, motivations, how we quantify diversity, 3 different perspectives that we have identified, empirical studies, and finally conclude our work. So let's start with motivations. So at the beginning, please read this short text taken from the public Wikipedia data sets. It is, your behavior is inappropriate and your reaction is exaggerated. I'm not sure if you should have administrator rights. So in general, can you say for sure whether it is aggressive or not? And I have a request to you. Please vote right now. So you can use the reaction icon in the bottom. So in the bottom there is I cannot show you this reaction button, and the green check means it is non-aggressive and acceptable for you, and the red icon with cross means it is really aggressive and rather not acceptable. Janek will count your votes in the participant window and inform us about the results. We can 2 votes at the moment, 3, 4, 5. Yeah, some people find it non-aggressive, but it is not 100%. Yes, could you please? At the bottom, it is reaction button, and there we sorry. Once again, it's my fault. Yeah?
Zaraz. Przepraszam, mam drobne pytanie z sali tutaj. Czy dałoby się coś zrobić z jakością dźwięku, bo bardzo słabo słychać faktycznie.
Okay.
Straszne są jakieś zakłócenia i nie wiemy, czy...
Może... Tak, Przemku, ja też u siebie słyszę, że jest tak...
And now, can you hear me better?
Tak, teraz jest dużo lepiej. Jest dużo lepiej.
Sorry, so I have used another mic from my equipment, so we can proceed. So if so, we can proceed with that. Okay, so let's go on, not to waste time. So the results on real data sets will be shown a bit later. In the common generalized approach, we assume that the given text can have only one class assigned. It is either offensive or non-offensive, and the same for all readers. However, our approach focuses on analyzing inconsistencies between annotators. This allows us to model and understand how a given user stands out from the others. And this is the key idea behind our new concept, which is called personalized natural language processing. First of all, we respect the feelings of the individuals. Our motivation comes from the observation that this is difficult to collect data that reflects perception and beliefs of all social groups. After all, these groups may have different opinions and worldviews. Besides, the commonly exploited generalized solutions are biased toward the mainstream. It means that some individuals are not respected, and therefore some users may lose their confidence in the system. Let's look what tasks are subjective and relevant to our research. Overall, we identify lots of subjective tasks in NLP. We expect that they lose a lot from the general mentioned before generalized approach. So firstly, we can consider the reader's subjective perspective. Here we have different emotions elicited by the text. Some content may be offensive, aggressive, hostile, funny, sarcastic, dismissive, and so on. We can also consider hope or supportive speech, unfair generalization, and even inflammatory text that trigger heated discussions, especially online. Even some positive and negative sentiment polarization may be treated differently by some companies. For example, those that use controversial messages on purpose. Besides, we can have subjective author perspectives, this one. It means that we can differently recognize author's intention. Or we can also consider generalization of the content in the individual and personalized way. Conversations combine these two approaches. And in our research, we focus primarily on the reader perspectives. And these three tasks, emotions, offensive, and humor, is within our recent interest. So as you may expect, some NLP tasks are subjective and diverse, so let's try to measure this diversity. In principle, we can observe that some messages are controversial. For that reason, we use entropy-based measure related to the text. So it quantifies how much all known annotators agree in perceptions of a given document. It is offensive or it is not offensive, or maybe 50-50. On the other hand, human-oriented measures consider how much a given person belongs to the mainstream. So we studied our own conformity measure and another based on Z-score. Yet another measure describes agreement level among all annotators for the whole collection of documents. Here we have pretty well-known Krippendorf's alpha and our modification of Fly's kappa. We called it wave kappa. It is Wrocław annotators variability estimator, so it is averaged for all different numbers of annotators per document. So let's try to explain them. The texts with the greatest disagreement between annotators in principle are most interesting. So they provide us with the most valuable information about the preferences of individual users. For this purpose, we developed this new measure, measure of conformity. Thanks to it, we know how much ambiguous opinions of a given document provokes. It ranges from 0 to 1, where 1 indicates greatest disagreement in the agreement, just like here, 50-50. Yeah? So we have 7 annotators that agrees that it is non-aggressive, and the same 7 it is non-aggressive, and it is real data taken from Wikipedia Detox. So it is not the same as your votes. On the other hand, if a text is more clearly aggressive or not, its controversy decreases. So in this example, we change only one word. We replace the soft inappropriate with much stronger terrible. Now the whole text sounds much more aggressive. This changed the distribution of user votes 2 against 12. And as a result, it significantly lowers the value of controversy. So the controversy is much smaller. But how can we represent people, the users? In order to model a user properly, it is very important to understand how unique their preferences are. For example, whether a given user often votes like the majority or like a minority. This tells us a lot about the user's individual profile. For this purpose, we created a measure called user conformity. It tells us how much the user behaves like the majority. So it is also between 0 and 1. It can be interpreted as the percentage of users. Here is the percentage of users who voted the same as a given user. So if a user voted the same as the half of the users, like here, then the conformity measures is 0.5. So these 2 users voted as the 50% of other users. Conformity can be for one or more classes, or for both classes. It means it can belong to the mainstream of offensive content or to the small minority of non-offensive text. It is aggregated over all previously known text annotated by the given user. So it belongs to so annotations of the user. If the user opinion is shared by the minority, the measure of conformity drops. look at this green user. He is not a part of the mainstream. Conformity is closer to 0. It's like here. The smaller the minority the user belongs to. If the group of people who vote like the user is the minority, then the conformity is closer to 1. And this red guy agrees with the mainstream, and the mainstream is greater, so his conformity is higher. In principle, we distinguished 3 views, 3 perspectives on perception of textual content. The first one is macroscopic perspective. It's here. It assumes that every human understands the text in the same way. This is only one label assigned to the text. For example, the text invokes an emotion of joy. Everybody is happy reading this text. It is macroscopic perception, and this is the common approach to NLP. To apply it, we need some trained or expert annotators able to annotate and represent the opinion of the whole society. And the only data we use to train and test is the content itself, possibly also the context. It's like the source of the context, the content. In the second, but mesoscopic perspective, we recognize some social groups. That is, here we have 3 groups. Each of such a group is treated separately. It means that the class labeled to the text represent these groups. So we have 3 labels, 1 for each of these groups. Each group member shares the same perception. Here we need additional data, like the identified group identifier coded with 1 hot, group demographic profile, or the group context. The group can be either predefined or extracted using clustering techniques. In principle, this is already a personalized method, but weakly personalized method. The third perspective, it is our main interest. It is human-centered. So, but not that the previous or this previous one, especially the first one, was data-centric. It is not human-centric, but data-centric. Our is human-centric. Here we have here each individual is treated independently and may receive different classes. It assumes that everybody is unique and may differently perceive the content. For that papers, we need some information about the given user, like behavior, demographics, social content, or even affective states. So in our studies, we exploited past user behavior in the form of previously annotated texts. We assume that it reflects user unique belief and well used. We can treat it as the kind of calibration. So since the classes are assigned independently for each individual, we do not need any generalized labels anymore. So we do not need an expert because every human is their own expert. We do not need an agreement procedure like majority vote either. So let's start with studies on data. So the first, yes, annotated data. So we investigated data detox dataset. It is a collection of textual discussion about the Wikipedia entries. This among Wikipedia editors. These comments were annotated using crowdsourcing by many people. The entire collection consists of 3 datasets: toxicity, aggregation, and attack. And the labels assigned to each annotator are the numbers from -3 to 3, but we transform them to the binary classes is toxic and it is not toxic. Therefore, about 40% of texts are controversial that have at least 1 different annotation. It means that 60%, the rest are purely non-toxic or purely non-toxic. Very few of them are purely toxic. Besides, we have aggression and attack data set. who have two classes, non-aggression and is aggressive, or is attack, is not attack. These two data sets share the same annotator, not all, and the same text. It means that the given text was annotated with respect to both its aggressiveness and attack. Only 2100 annotators had at least one annotation and demographic profile provided, so we needed to remove some annotators together with their annotation, so that's why the annotation number decreased. Even though the number of texts remained the same after this preprocessing procedure. So let's start from aggressive data set. It contains about 100,000 comments and in average of 10 annotations per document provided by 2100 individuals. About 18% of the annotations were aggressive only, so the collection was imbalanced. About 50% of all annotations were controversial. It is these texts that had at least one other annotation assigned. So it means that this 50% of text require a more personalized solutions. Yeah? So it is not so clear whether it is aggressive or not. So for our purpose, we developed some methods. But before that, we would like to tell you a little bit about the data split. So the Wikipedia data, this detox data has its own train dev test split. So we kept it to facilitate the reproducibility of our study. So division is represented by columns. So each column it is one text. Since we want to operate on humans' text perceptions, we divided the data by users, which are rows. So each row is one user. It means that the different users and their annotations were used for training. It is this part, and different for testing. So we split by users. Besides the text from the dev set, it is here, were used to compute user conformity mentioned before, either for training, it is this part. It is treated like previous annotations of a given user. It was performed on the separate set of text, it is this dev, and the same text, also from dev, were used for testing, also to calculate conformity measure. It is this light blue area. The reasoning quality was estimated on using separate texts. Yeah, it is from the test. And for users not used for training. It is this set of users instead of which was used for this was for training and this was for testing. As a result, of course, some data with this wide background was not used at all. And note that such a validation split according to users rather than to text is our unique approach, not exploited in other NLP tasks. So we haven't found it in any literature like this. So having the data, we can proceed with the methods. Before we describe our own methods, let's look at the generalized data-centric methods commonly used in NLP. It means that we have only one agreed class label achieved commonly by majority voting. Each user received the same decision from the model. It also means that for all controversial text, some users will obtain the wrong prediction, because the prediction is the same for all. So some who have another perception it doesn't matter whether the model will decide correctly the majority, but also this minority, either this majority will be wrongly predicted. But it is our baseline, so we want to reference it. To exploit personal characteristic, we created 3 user-oriented methods. It is the first one. It provides the value of the conformity measure for each user with respect to their votes on non-aggressive and aggressive text previously known. Yes, it is from this dev text. In conformity-based personalization, we use 6 simple measures of conformity that represent the beliefs of a single user. It is general conformity and wider conformity. Each of these can provide 3 separate values for aggressive and for aggressive text only, for non-aggressive text only, and for both types of text. Finally, we examine input feature set based on the general conformity only, weighted conformity only, and for both measures. It means that for each user, we have 6 static numbers describing user beliefs, which were used directly in the input of the model together with the regular embeddings, text embeddings. The second model builds a separate representation of the text that the user has rated as non-aggressive or aggressive. It means that we send 2 additional embeddings to the input. The first one is computed as the average embeddings of the text annotated as non-aggressive, and this is the average representation of all text seen by the user as aggressive. As a result, the size of the input is 3 times larger than for the baseline. The third method takes into account separate representations for each of the texts annotated previously by the user in the past. Note that the input size is flexible and relatively large. For example, 10 texts annotated by the user in the past, we have 11 times larger representation than for the baseline. So this personalization features are computed only once for a given user based on this previous knowledge, previous annotated text. So go to the results. So during the evaluation, we compared the effectiveness of our methods. It is one of our this orange line, and generalized opinion. It is the upper green, the red line. As you can see, the essential increase is already observed for personal embeddings created using only one single text. So we used fast text and logistic regression in this particular result. Very similar phenomena and almost the same increases were observed for BERT, the Roberta, XLM, Roberta, and LSTM. Details are in our paper. So the differences between language models mentioned for this like BERT, Roberta, and so on were less than 2 percentage points. So, and always our personalized methods were significantly better than the generalized baseline. We found that using information from only 4, it is here, user-rated text significantly improves the quality of inference. The annotation-based embedding, it is this with triangles. In general, performs significantly better than the others. The conformity-based solution outperforms this personal class-based, since this size of these embeddings, or size of the collection used for calculation of controversial values as the level of 8. As said before, all our methods better result than the generalized methods, which is this right line at the bottom. As expected, the main gain is provided for controversial text. So it is the buckets of text with the most controversial, it is on the right side hand, and the least controversial text, it is on the left hand side. And here, for the more controversial or most controversial text available in the data sets, the gain is greater. And there was very little controversy for the first 50% of text. It is this part of the chart. As the side effect, we analyzed document and human embeddings. We found that some annotators process very small standard deviation in their annotations. It is quite suspicious, and it may be a sign of fraudulent annotations. It was crowdsourcing. Yeah. So nobody has discussed this before for this data set, so it was pretty strange for us. Unfortunately, it referred to only a small fraction of the entire data set, so it is not so significant. So we do not expect that it is, even if it is fraudulent, so it impacted on the final results. Additionally, we analyzed the embeddings, word embeddings, and this revealed quite interesting word cluster. It is this cluster relevant to the domain set. It is about aggression. So here you can see the words related to aggressions. So I think it is quite reasonable, and I wouldn't read it, but as you can see, it is aggressive vocabulary. A similar result of words linked to the attack. It is another cluster identified here. It is attack. You can read these words. And most of us would agree that it is really the words that can be the sign of attack. It comes directly from our analysis of our embedding. For toxicity, it is slightly different. It is toxic text. So for toxic text, you can clearly see also some results. So that's all from my side. So now Janek Kocoń takes over the presentation. So Janek, it is your turn.
Thank you. So I'll switch the screen.
Yes, you're welcome.
The only thing is that I need the permission for sharing the screen. Maciej, are you here with us?
Jestem, tylko co muszę zrobić teraz właściwie, bo u ciebie nie widzę przy tobie.
All right, so maybe let's assume that...
Security guard at the bottom.
Ask to start video? Nie, to mogę zrobić?
No, allow sharing. Enable sharing.
Enable sharing. Mogę zrobić make host na pewno, ale nie widzę enable sharing.
All right, so let's make a host right now, and I'll turn this on for me. Good. Probably no one else would like to start to join our presentation right now, so maybe I'll leave with the host. All right, so let me share the screen. Wait a second. Okay, are you able to see the screen?
Yes.
Yes, it's okay.
Good. All right, so in this section, I'll present the research on the personalized models in the emotion recognition task. And we presented the results of some of this work at the ACL conference this year, and we'll be presenting the rest at the ICDM conference in December. And I'll start with the results of the first paper, in which we focused on creating a method for predicting the emotions aroused in a particular text recipient. So the model I will be discussing gets a new feature as input, in addition to the text representation itself, which is the personal emotional bias. And this feature is computed based on a specific human's past decisions. So in this approach, we also do not average the ratings of all annotators within the text, but rather consider each annotation individually in the context of a particular person. Yeah, and more specifically, his or her emotional bias. So the data set that was used in this research was created as a part of the Sentimenti project. And we used a part of the data set where almost 9,000 people evaluated 7,000 texts. And each text was rated by about 50 people. Also, each person for each text rated 8 basic emotions from Plachik's model on a scale, as well as the valence and arousal on the text. So the total number of annotations here is nearly 4 million. Yeah. Also, due to the commercial nature of the project, this data set is not publicly available. And the texts in the data set are mainly reviews of hotels and doctors. On the slide, you can see a sample opinion about the hotel, and below the text, the interface for the annotation. So the values on the scales were taken from the data set and are the actual ratings for a particular person. Yeah. On the right, here are the distributions for all the ratings the text received from 54 people. And the red dotted line represents a value of 0. So based on the analysis of these distributions, we can say that most people evaluated this text positively. Yeah. On the other hand, the distributions present a certain decision spectrum. Yeah. So even if our majority and overall observation is true, there are still some differences in people's individual judgments, yeah, about the intensity of the emotions they felt. So here we can see another example of a rating distribution for a short text. So the first 4 rows here represent positive emotions. The next 4 distributions represent negative emotions. And then we have a valence, yeah, where the left side of the scale is negative, the middle one is neutral, and the right side is positive. So the last scale represents emotional arousal values. And as you can see, this text was also rated mostly positive. Yeah. However, there are also some people who perceive this opinion as negative, as you can see here. So the example mentioned just a moment ago with the distribution of answers has average values as shown on this slide. Yeah, on the right-hand side slide for all 8 basic emotions, and also as blue pointers on the scale. Yeah, so scales presented here are the same that were used for gathering the data during the survey. And now let's look at some interesting things. So the red pointers right now here on the scale correspond to a person we call John. Yeah, so these are John's answers, and they're also here visible as the digits on the most right-hand side. Yeah, and as we can see, John's answers are very close to the average. Yeah, that is to most of the respondents. So here you can also see for the first time the formula we propose to calculate the personal emotional bias. And it's actually an aggregated z-score of the user's answers with respect to other users in the given subset of documents, which we called past dataset. Yeah, past meaning that it contains information about users' ratings we already know. And in this particular example, z-score of John's answers is low. Yeah, so therefore, his personal emotional bias is also low. And we may say that John is an emotional conformist. Yeah, so we may say even that he goes with the mainstream. All right, but here we have another person. Let's call it Bob. Yeah, so now light blue pointers and the most right-hand side of the scale, it shows that Bob's answers. Yeah, so Bob's text perception is far away from the average. Yeah, remember that average is that dark blue pointer. So z-score of his answer is high. Yeah, and therefore also his personal emotional bias allows us to predict his answers more precisely. Yeah, so the model without that information cannot predict, let's say, values similar to his, right? Okay, so we performed our experiments on 2 types of machine learning tasks. So the first one is a multitask classification, and here we are trying to, for each task, we predict an accurate and actually discrete answer for each emotional category. So if a person, for example, for the emotion sadness, has got to rate it, giving one of these 5 potential answers, so we are trying to predict the exact answer of that person. So for example, 4. Yeah. And the second one is a multivariate regression. So the task was to estimate the numerical value for each emotional category. And the difference from this previous approach is that in the second approach, we take into account the distances between user ratings. Yeah. So here, if, for example, person said 4, but we guess 3, it's wrong. Yeah. But in case of regression, 3 may be closer to 4 rather than 2, for example. Yeah. So that's the difference. And also, the very important thing from the perspective of the evaluation is the data split. Yeah. So as you probably remember from the previous slides, in the case of experiments we did for offensive speech recognition, there was no user-based split. Yeah. So it means that we had the same users in train and test set. Here, the situation is a little bit different. Yeah. So we have 2 dimensions for our split. So the first one, yeah, is user-based. So we split the data set into 10 folds, yeah, and each fold contains unique users, yeah. And also within each fold, we have text-based split into 4 parts. So these parts are past, present, future 1, and future 2. And this past part is used only to calculate the personal emotional bias, yeah, for users in train, dev, and test sets, respectively. And we treat it as text already annotated by users. Yeah, so think of it as a kind of knowledge base, yeah, about their decisions. And then we have we actually train the model on a training set, yeah, of text and users. But during the training, we evaluate the quality of a model in each epoch on a dev, let's say dev/future 1 set, this one, yeah, which contains different users and texts, yeah. So in that way, we look for the best model, which is not dependent on both texts and users, yeah. And we also look for the model which finds the general dependency between personal bias and potential text scoring, yeah. And we do also this in the context of deep text representation, which is taken from the given language model. Finally, we test the model we found on a test/future 2 set here. So this final evaluation is a simulation of potential new users evaluating new texts, yeah? And the only thing we know about them, yeah, is their personal bias calculated from texts annotated by them in the test/past dataset here, yeah? So this explains also the meaning of past word here in the equation. All right, so now let's move on to the description of methods we used in the research. So we evaluated 2 approaches, explained also within the previous research. Yeah, so the first one is a generalized reasoning, which does not take into account the context of the user. And the second approach is using the information about the user. Yeah, so in that way, we can see that what is the potential gain we may have if we consider the human context here. All right, and we combined the data from all individual answers with additional data like demographics and also the personal bias. So this data was the input for classification or regression models. And the developed method is predicting the perception of text-related emotions, yeah? And the goal is to reflect the reactions of a given reader. So the classical approaches utilize only texts in the model, but we extended with user-based features. Yeah. So in this way, we switched from averaging labels for annotated texts to rather considering individual text annotations. One of our baseline models was taking the text embedding only as the input. Yeah. And also the machine learning multitask model was predicting the values for all emotional dimensions at the same time. We tested bidirectional long short-term memory and also multi-layer perceptron-based networks, and it was depending on the different types of embeddings. I'll talk about this a little bit later. All right, we also take into consideration additional attributes by adding them as enlarged input into neural network models. So we were extending the text embedding here, yeah, with the information about the user demographics, also its personal emotional bias, and also all these features combined. So that's the extension of the previous baseline architecture. And now let's look at the results we obtained. So here you can see the emotion classification results for the best text embedding model, which was Herbert, also with additional fully connected network for the classification task. And we tested 6 approaches, starting from the most basic one, which was the average value for each emotion, also calculated on a training set. And actually, this was the worst one. The second baseline was a text-based only model, which represents a popular and generalized approach, and it's often used currently in NLP. Yeah. The third result was the extension of the text model with the information about the demographics. So as you can see, we observe a significant gain, but then we have a text plus personal emotional bias model, yeah, which takes both a textual representation and also the personal emotional bias. So comparing to our baseline, yeah, we can observe a huge increase, yeah. So it's over 20 percentage points of gain, yeah. And adding the demographics features here, as you can see, to this previous model, actually it gives the additional 0.4 increase, yeah, but it's actually not significant. So let's have a closer look at 3 selected emotional dimensions, which are joy, surprise, and valence. Yeah. So we take only 2 models, yeah, our text baseline and also the extension of it with personal emotional bias. So in case of emotions, the observed increase is the largest. Yeah. For more general dimensions like valence, for instance, yeah, it actually strongly correlates with sentiment, so the gain is smaller. Yeah, so we may say the more obvious the dimension, the lower the gain in case of personalized approaches. Yeah. So this gain is about 14 percentage points. And in case of the remaining emotions, you may see even gain like 23 percentage points. But it's also important to know that classification here is a really hard task. Yeah, because we are guessing the actual value of a person set on a scale for each emotion. Yeah, so we're pretty sure that probably the same person couldn't even reproduce their own results if we would ask the same person to annotate the same text another time. Yeah, so actually the regression task allows to determine how closely the model predicted the correct answer. Yeah, and it's actually much more meaningful to us. Yeah, because it's not really important whether the person said that, for example, the joy in their perception was equal to 4 or to 3. Yeah, the more important is that there was more or less joy in their perception of the task. Yeah. Okay, so in the case of for our text plus personal bias, we observe actually more than 30 percentage points increase with respect to the baseline model. Yeah, and it's actually our increase in the R squared, yeah, comparing to the text baseline. So it's worth mentioning that also other language models were slightly worse than Herbert, but we talk about 3 percentage point differences, yeah, and these differences were observed similarly for each of the models we were testing, yeah. So these tremendous gains are actually observable for all the models I mentioned here, yeah. So it's independent on the language model we choose. And there are also some emotional dimensions for which the gain for the emotional bias based model was even larger than 40 percentage points. So it's very huge increase. Yeah. What else? We also evaluated the impact on the number of texts in our past data set, yeah, on the basis of which we calculate the personal emotional bias. And on the chart, you can see a baseline here as the blue dashed line on the bottom. And we have a number of texts here used to calculate the personal bias on the x-axis, yeah? And also on the y-axis, there is the R squared value. And we can see that the information just for the single document is enough to make a significant increase in the quality of the personal bias-based model. Yeah. One of the important things is the gain is even larger if we select the most controversial documents first. Yeah, so that's the blue line on this chart. And actually, the more text we take for calculating our personal bias, the less important their controversy is. Yeah, so we see that when we want to know something about user, it's better to start from the most controversial text. We also have discovered a nearly linear negative correlation between annotator's agreement level, calculated as Krippendorff alpha coefficient, and also the performance of the regression model based only on the personal bias, with no textual information at all. Yeah, so each data point actually corresponds to a separate emotional category. And actually, concluding this part, we were able to significantly improve the prediction of emotions evoked by the given textual opinion in different people. And the most important is that the use of our proposed personal emotional bias measure allows for a tremendous gain in prediction scores for particular annotator. Yeah, so this opens up the possibility of creating a dedicated and personalized solutions targeted at specific social groups, yeah, and also specific individuals we want to reach with a given message. And now I present the latest research, which results will be presented this year at the International Conference on Data Mining. So this is the extension of the previous research for other datasets, yeah? And also with new personalized architectures. Here, we decided to rename our personal emotional bias measure from the previous paper, yeah? And now it's called a human bias. The reason is that this measure is task independent, actually. And I'll prove this in a moment, yeah? So now let's start with the description of new architectures. Okay, so you may see 3 different models here, all in the one picture though. So the first one is a baseline textual architecture known from the previous paper with no personalization. Here it is in this green frame, yeah. 2 other models share mostly the same architecture. So this the extension to the baseline. The only difference is the additional feature. Yeah, so it can be the user ID provided as a one-hot vector, yeah, or the calculated human bias feature. So it is known previously as personal emotional bias, which is actually a single number. And we called this last model, the common one, yeah, a Hubie formula, which stands from human bias formula, as the feature is calculated directly from the data using the equation we already know. And then we have a new architecture, yeah, which is called Hubie Simple. And this is a model inspired by the solutions known from the recommender systems. So the model predicts the label, yeah, as a sum of 3 components. So it's a textual content, actually the text embedding, human bias, yeah, and some of the word biases, yeah. So the textual content representation is provided in the same way like in non-personalized models. And the model additionally manages a real valued numbers, I mean biases, yeah, for each human, and also for each word in all texts in the dataset. So in the case of a multitask classification, yeah, or regression, each human and word has separate biases for each task. And before the training, biases here and here are randomly initialized and also optimized with the backpropagation during the training. So the human bias can be considered as a simple prediction adjustment for a particular human. Yeah, so it's not calculated, it's learned. And after the training, the bias for each human is constant and also does not depend on the text being evaluated. Yeah. So the major advantage of this model is that no feature engineering is required to find a good representation of the user. Yeah. So we don't have the formula, we rather learn the representation of the user from the data. And when a new user or annotation is added to the data set, it is not necessary to retrain the entire model. Yeah. Actually, instead, the model can be fed only with new examples, so our individuals can optimize their human bias value, yeah, with the rest of the model parameters which held constant. And actually, to model the multidimensional subjectivity of the annotator, we also introduce a model that optimizes multidimensional latent vector of an annotator that captures his approach to the concept of the interest. And this model is also based on the techniques known from the recommender systems, which mostly are called neural collaborative filtering. Yeah. And the main problem in directly applying NCF to the model of to model an annotator perspective is something we know from the literature as a cold start problem. And this problem is mostly can be found in most crowdsourcing based datasets. And I mean that most texts in this dataset typically contain only few annotations. Yeah. And it makes it very difficult to build a good representation of such texts and annotators from scratch. Yeah. Also, in addition, new texts for which we do not have annotations often appear in the production environment. Yeah, if we have our system ready developed. Yeah, so the model cannot generalize to new samples. And to overcome this problem, we propose an alternative and actually hybrid model, yeah, that uses language model representations, yeah, of texts, and also uses optimizes only the annotator latent vector. So this is the main difference of this model with respect to NCFs, yeah, but which actually typically create a representation of both the user and the item, which here is the text. Yeah. So the difference with the previous model, which was Hubie Simple, yeah, is that it manages a real valued and custom latent vector for each annotator in the dataset. And also this vector is initialized randomly and optimized during the training using backpropagation. Also, to capture the relationship between the annotator and the texts being evaluated, the annotator embedding is multiplied, it's element-wise multiplication with the text embedding, and this new vector is fed to fully connected layer to predict the label. Similar to the previous method, we managed to separate bias for each word in the dataset. It's here. The last model extends the Hubie medium model with additional trainable word embeddings. Since words are common to different texts, they are much better represented in the dataset compared to the whole texts. Yeah. So this allows their embeddings to be trained with lower risk of overfitting. Yeah. And also to generalize to new unseen texts, since they typically contain the same words. And this model captures not only the annotator's views for the entire text, yeah, but also individual words. So this approach seems to be justified, especially when dealing with words that are, for example, offensive only to the certain social or religious groups. Now let's look at the results. And this time we evaluate our architectures on 4 datasets. So 3 of them are a part of Wikidetox, and the last one is the emotions dataset. And I will start with a very interesting observation regarding the comparison of the calculated human bias and learned human bias. So here we can see a strong correlation, yeah, between bias calculated using Hubie formula, yeah, and bias learned by Hubie simple model. So first of all, we can see a very high correlation among positive emotions, that's this top left green square, as well as for negative emotions. Yeah, so that's bottom right blue square. For most of the emotional dimensions, learned and calculated biases are very highly correlated. Yeah, so this correlation value is above 90%. So our intuition when we created the formula is proved right now by observation of the learned biases. Here you can see the results obtained on 3 datasets within the Wikidetox. So that's for attack, aggression, and toxicity. And it is worth recalling that there were not many controversial texts in this collection. Yeah. And nevertheless, we observe a statistically significant gains in quality related to the baseline, right? And we measured it using the F1 score for the positive class. And actually, this measure is the most difficult for these data sets, yeah, because they are highly unbalanced and the number of positive classes is rather small in the whole data set. These differences were observed regardless of the text representation model chosen. So the differences between text representations were much smaller than those between our proposed architectures within a given language model. Yeah? So we may say that actually our architectures are independent on the language model we choose. Also, the same conclusion applies to the emotions dataset. But here, actually, the differences between the baseline and the other personalized architectures are much larger. So within the personalized architectures themselves, the tendency is that the more complex the architecture, the better the results. Even so, these differences are not that large. Also, the findings regarding the different language models used to represent the text are also similar for the emotions dataset. Yeah. So the results are comparable here. And the main conclusion is that our architectures are largely independent on the language model used. Yeah? At least when we compare transformer-based solutions, right? Now, let's look at the training time for the presented architectures. Yeah. So the most complex personalized model takes several times longer to train than the baseline. But for the simpler models, these differences are not as large. And also for some models, the human information provided in a simplified way makes the training time faster than the baseline. Yeah. So hence the conclusion that human information can also speed up the training. However, the inference time is shortest for the baseline model, which must be considered in the context of production solutions, right? So again, it can be seen that the more complex the architecture, the longer the inference time, resulting directly from the larger number of parameters of the complex model, right? And now a few words to summarize our presentation today. So we have proposed and tested several new human-oriented methods, which are actually suitable for various problems in the text processing. So the results of the conducted research validated our general and novel idea to apply primary personalized methods for subjective tasks in NLP. And the significant impact of personalized representations on the model performance is actually directly evident here. Yeah. So the conformity, controversy, and also personal human bias can be obtained either using a formula we have developed, or in the case of human bias, by the training of the latent representation of the user. In all cases, it delivers important information about the user. Moreover, only a few annotated documents, like 4 up to 6, yeah, is enough to significantly improve the recognition quality for a specific person. And this is true regardless of the language model we choose. Also, it is very important in the validation process to properly split the dataset by users, yeah, to simulate the process of new users appearing in the system, and also new knowledge about them appearing in the form of annotation of new texts. We already know that even fairly complex demographic data do not allow us to make as large gains in the quality of inference as the knowledge associated with the subjective task we are solving in the context of a human. Yeah. However, there are now not many data sets in NLP for which personalized models can be created. Hence, it is very important to consider humans when creating new data sets, yeah? And also to collect multiple annotations from multiple people. So this is especially important in subjective tasks, yeah, such as recognition of hate speech, emotion, humor, sarcasm, right? In other words, anywhere where we as humans are naturally different, yeah. And we believe that this approach can make artificial intelligence also more human-like, yeah, and also able to incorporate the personality of the individual into decision, yeah. All right, and also that's our team within which we conduct our research. So this presentation was made by all the members, which are Przemysław Kazienko, Jan Kocoń, Kamil Kanclerz, Julita Bielaniewicz, Marcin Gruza, and Piotr Niukowski. Also, these are the articles on which the presentation was based. So the first 3 are already available online, while the last one will be available in December. And here is the take-home message. So personalized NLP is much better than generalized for all subjective tasks. Thank you for your attention.